let's talk about our first specific example of a force and how to handle one specific force. And this is going to be gravity. So we're not going to attempt here to do a generalized version of gravity that will work for like astronomical contexts and stuff like that to explain why the Earth revolves around the sun and all that type of stuff. We're just going to do everyday cases of gravity. Where you're near the surface of the Earth and you know, you're not doing anything crazy. In this case, the force of gravity is extremely simple. Near the surface of the Earth, gravity is a constant force. It has magnitude equal to m times g, where m is the object's mass, the object who the gravitational force is acting on, and g is a constant number which depends on the properties of the Earth in this case, since the Earth is the one doing the attracting. So basically m is the properties of the object which is being pulled down. G is the properties of the Earth, you know, which is kind of doing the pulling. And the value of G in SI units is about 9.8 meters per square second. So that's the magnitude of the vector. The direction of the vector equals down towards the center of the Earth. Okay. So this vector is constant in both magnitude and direction, crucially. Okay, so those are the basic properties of the gravitational force. I want to show you really quickly what some of the really basic consequences of that force are and how it connects to what we were just doing. So just take a really simple situation. Let's say, for instance, I take this ball and I release it under the influence of gravity, and gravity causes it to fall down. What's going on there? So we have an object. There's my ball. We draw a free body diagram of that object, first and foremost. That's step one of understanding the ball's motion. Draw a free body diagram. So there is one force acting on the ball. It is pointing straight down, as we just said there, and the magnitude of this force, so this is the gravitational force, and the magnitude of the gravitational force, as we just said, is equal to mg. Okay. Now, this is the world's simplest free body diagram. Let us now apply F equals ma to this. And just to be pedantically careful, I'm going to treat this as a two-dimensional problem, just to show you very carefully what happens. In the x direction, there are no forces acting on the object. There are no forces with x components in this problem. In the y direction, the sum of the forces in the y direction is just simply minus, because it's pointing downwards, m times g, because that's the value of the gravitational force. Now we set this equal to ma, so we have 0 equals max, which tells me that the acceleration of the ball in the x direction will be 0. And in the y direction, we will have minus mg equals ma y. And right away, you notice something extremely interesting happens, which is the mass of the object cancels out. So this tells me that actually the mass of the object, surprisingly, will not influence its acceleration, will not influence how fast it falls. And you can actually see that really quickly with just an experiment. Just grab two random objects near you. Just don't pick anything like a sheet of paper where air resistance is going to be a major factor. If you just grab two random objects and drop them at the same time, you'll find that they fall at the same rate, even if they are quite different in mass and shape and size and things like that. So first of all, Conclusion number one, the mass actually cancels out if gravity is the only force acting on the object. So objects with different mass will fall at the same rate. And furthermore, and even more specifically, we end up getting the conclusion that the y component of the object's acceleration is negative 9.8 meters per square second, negative g. So the acceleration of any object, I didn't actually, I mean, I was thinking about this ball in my mind when I did this problem, but none of the ball's properties actually came into the problem because its only property of any significance was its mass, and that canceled out. So this is actually true for just about any object. As long as gravity is the only force acting on the object, it's true of any object, that different objects will fall at the same rate due to gravity, and the rate that they fall is given by an acceleration of g pointed straight down, and they will not have any acceleration in the other direction. Okay, and that's the basic conclusion of the way things fall under the influence of gravity. That's the basics. In the next video, let me walk you through kind of how we can use this information and connect it to what we were doing a little bit earlier.